In this video for section 7.2, we're going to introduce the idea of a sampling distribution. And so we're going to think about when we make decisions based on sample rather than an entire population, what kind of questions that brings about. And so here are a couple of examples. If we have a director of tourism in a Caribbean country that's conducting a survey of 780 adult visitors, and it shows that their mean daily expenditure is $318.69. Is the actual population mean, or the average mean daily expenditure of every single person who visits the country, going to be exactly $318.69? Probably not exactly, but how close should we expect it to be? Here's another example. We have a quality engineer for a furniture manufacturer. They're testing 150 pieces, and they find that 15 of the pieces had one or more issues. So that's 10%. Does that mean that 10% of all of the pieces made had issues? And if not, what could the actual value be? Should we be testing more than 150 pieces? So remember that we use samples when getting data from the entire population would be really expensive or really difficult. It would be really difficult to survey every single person who visits the country. And it would be really difficult or expensive to test all 6,900 pieces of furniture. That's why we use a sample in the first place. But anytime we're doing a sample, there are many, many possible samples. So thinking about with 6,900 pieces of furniture, I can make many, many different groups of 150 pieces out of that larger group. And each of those samples would contain different items. And because of this, our sample means and our sample percentages will be different. I could get 8% of the pieces that had issues, or I could get 12% if I had a different sample. So it really just depends on which 150 I happen to be taking. So the sampling distribution is what describes this distribution of possible sample outcomes. So looking at theorem 3, if we have a population that's normally distributed with a mean mu and a standard deviation sigma, our sampling distribution of the sample mean is also normally distributed with the same mean as the population mean. The standard deviation, however, is different. For the standard deviation, we take the standard deviation of the population and divide it by square root of the sample size. And the reason for that is that as we increase our sample size, our standard deviation is going to get smaller. So thinking about this furniture example, if I were to only pull 10 pieces, I could have a lot of variability in the percentage that have issues. I could have a sample of 10 where 0 have issues, or I could have a sample of 10 where 80% of them have issues. But as I increase the number that I am putting into my group, I should expect the percentage that have issues to get closer to the actual value of the population. So we're going to look at an example here. This is the West Side Drive-In. Lunch orders average $12.50 per customer with a standard deviation of $5.50. For a random sample of 100 customers, what is the probability that the mean will fall between $12.25 and $13? So this should look similar to some of the normal distribution problems that we saw earlier, but there's a little bit of a difference because we are looking at a sample of 100 customers, not just an individual customer. What is the probability that it will fall between $12.25 and $13? So my mean here is going to be the same as the mean for the population. So that's $12.50. But for my standard deviation, I'm going to take my standard deviation and divide by square root of the sample size, which is 100. So there's a correction that you're making basically to the standard deviation to account for the group size or the sample size. Now this problem, it works out nicely because the square root of 100 is 10, and 550 divided by 10 is 55 cents. Now, most of the time, the problems won't work out nicely like this. You'll take the square root of this number, you'll get a some kind of decimal number. When you divide, you'll get some kind of decimal number that has a lot of digits after the decimal point. I highly recommend keeping at least 4, and it's better to keep 5 or 6 in your standard deviation that you write here and when you enter it into Minitab. If you round too soon, then that could make it so that your answer is off just enough that it gets marked wrong in MyLab, even if you're using the correct process. So that's my mean and standard deviation. I want to know the probability that the mean will fall between $12.25 and $13 here. And so this is going to be a middle situation in Minitab between those two numbers. So let's go to Minitab here and we will put this in. Again, we are going to graph, and down to probability distribution plot, view probability. And we are working with the normal distribution still. So our mean, $12.50, and our standard deviation of 55 cents. So again, mean from the problem, standard deviation we have to calculate using that formula, standard deviation divided by square root of the sample size. This is a middle problem, and we are doing specified x values between $12.25 and $13. Click OK. And here is my graph. So I can see that I have shaded the area between $12.25 and $13. I have my mean and standard deviation here. My answer is above the shaded area, 0.4936. So it's about a 50% probability, and it should kind of make sense that if you are looking at an area that contains the mean, and you also are kind of taking the standard deviation into account, but the mean is kind of the peak, so it should make sense that that's where it's more likely. So 0.4936 is my answer here. Again, pay attention to rounding in terms of entering answers. So when you're using Minitab in these probability problems, what we've been talking about for the last few sections, binomial distribution is what you are going to use if you are given number of trials and probability of success. Normal distribution is used when you are given a mean and a standard deviation. If you are given mean, standard deviation, and a sample size, then you are going to use the normal distribution and calculate the standard deviation using the formula of sigma divided by square root of n. So this formula here is really important to keep track of when you're doing problems in this section.